Ladies and gentlemen, I'm Serge Kernbach from the research laboratory in Stuttgart, Germany. We specialize in electrochemical measurements related to fluids, water, organic tissues. We are generally involved in research on biological and biohybrid systems. This video is recorded for Pegasus Aqua Seminar, and I will speak about electrochemical measurements in application to water treatment technologies, and in particular about MRET technology developed by Igor Smirnov, which is devoted to physical treatment of fluid. This is really short presentation. I have only 15 minutes, and I will try to answer three following questions. First of all, why chemically identical fluids can have different physical properties and interact differently with biochemical and biological systems. Second question, how to measure, but measuring mean two issues: how to detect and how to characterize such different physical properties of fluids. And finally, what is a concrete approach, what we suggest for MRET water treatment technology that we explored in our laboratory. First of all, I would like to say some words about electrochemical methods. Electrochemical measurements are a popular technology for measuring properties of fluidic and organic systems. It can be used also, for instance, for biosensing. This technology combines both physics and chemistry, and it was developed mostly during last 30 years. There are different electrochemical methods. In this talk, I focus mostly on impedance spectroscopy. If we look for terminology electrochemical impedance spectroscopy in Google Scholar, we will receive about 1 million of appearances. It means there is a lot of development in the community. There is an excellent review of impedance spectroscopy published in Nature this year. I would definitely recommend this publication. There is also a number of different books and popular manuals. As you know, fluids consist of molecules. But these molecules, they exist mostly in the form of ions. Ions are related to the number of electrons in the atom, and electrons have a negative charge and protons have a positive charge. And the point is that during electrochemical interactions, electrons can be transmitted from one molecule to another molecule, and in this way we receive in the fluid positively charged molecules and negatively charged molecules. So usually we call these molecules as cation or anions. So we characterize fluids by a specific charge of ions, number of different ions, and their mobility. Generally, electrochemical properties can be expressed in many different ways. For instance, because ions conduct current, we can measure this current in the way, for instance, if we put here two electrodes and create electrical field between electrodes, ions will carry electrical charge, and we will record current, electrical current, and in this way we measure a conductivity, electrical conductivity of fluids. Another example is a hydrogen index that specified acidity or basicity of a solution. This index is in fact specified by a relationship between hydrogen ions and hydroxide ions. So this, as you know, this index is important for biochemical reactions. Another important parameter is redox potential. that specified reduction and oxidation processes that are also important, for instance, for biological systems. Important point here that properties of fluids, for instance, how fluids interact in biochemical reactions, or how this fluid interact with different biological system. So these properties are defined not only by the chemistry of these molecules, but also by physical interaction between ions. Generally, there is a lot of different physical effects that influence properties of fluids. First of all, we should mention here near surface effects, what are, for instance, important for biological membranes. Here we find easy water, what was discovered by Jerry Pollack, that it also contribute to physical properties. Currently, we also know about 6 quantum effects. For instance, proton tunneling effects or self-ionization, and all of them also influence the properties of fluids. So the second important point here is that all these additional phenomena, they influence ionic properties. For instance, they influence ionic dynamics, and by measuring this ionic dynamics, we can also specify and characterize all these additional effects. We can investigate these phenomena by measuring electrochemical properties of fluids. Here I would like to mention one specific phenomenon. We currently think that exactly this phenomenon can explain different physical effects what we observe in the water. And as I said in the previous slides, fluids, they have different quantum effects, and one of these effects is related to orbital spins of protons in the water molecules. Rotation of protons can have the same direction, so we speak about orta molecules or orta water. If the spin have different directions or different spins, then we speak about para molecules. So this is the same water molecules, but they have different spins in the proton rotation. So observation, what's recently published, is that orta and para water have different chemical properties. For instance, para water is about 30% faster in a different reaction than the orta water. So I would like to stress this point again, that the same chemical elements demonstrate a different chemical activity. And so now we can return to the first point of this presentation. If we make a physical treatment of the water, so we apply different physical approaches and influence water in that way. So chemically, fluids remain the same, but we change physical properties, for instance, that reflect in different rotation of spins, and so we receive different physical properties in the fluid, and this fluid will differently interact with biological systems. So here the main question would remain how to measure the physical properties, because if we apply the classical chemical analysis, because we have the same elements, this analysis will not provide us any useful result. For testing physical properties of solutions, we apply electrochemical measurement, so specific form of electrochemical measurements, impedance spectroscopy with additional excitation. I already said in the previous slides that in the classical schemes of impedance measurements, we apply excitation potential between two electrodes or several electrodes, and record a current that flow between these electrodes. So we apply a specific excitation potential with a specific waveform and record response current. We analyze shape, amplitude, phase of this response signal. We analyze electrochemical noise and can calculate different properties of fluids. So this approach alone is powerful enough to specify the difference between treated and non-treated fluids. We can even provide some numerical parameters, so we can solve both the problem of detection and the problem of characterization of this difference. But here, if we would like to characterize different additional effects, we need to introduce additional excitation. So here we use for this additional optical, magnetic, thermal or electrical field excitation for these fluidic samples during measurements. So this essentially increased not only the sensitivity of this approach, but here we can extract additional information how the samples behave for specific treatment strategy. We applied these methods for fluids treated by MRET technology. We performed, in fact, only a couple of measurements. It was not a systematic study. We didn't receive any funding or any money for this measurement. It was mostly driven by our curiosity. And this example can be considered as a measurement technology for any other treatment approaches or physical treatment approaches. Here in this specific case, we used thermal excitation. This thermal impulse was applied here. This impulse was generated by infrared light by 940 nanometers. It seems this technology is sensitive exactly to this light spectrum. And even before application of this impulse, of this excitation, we see very different electrochemical dynamics in the background region. So you see here in the experimental sample and the control sample quite different dynamics, and after application of this thermal excitation, of thermal and optical excitation, you see very different dynamics. So this is a simple and fast methods if you would like to see or to demonstrate somebody else differences in physical properties between treated and non-treated samples. But here we can also perform more exact characterization based, for instance, on different frequency spectra here in this area, or temporal dynamics of these frequencies or electrochemical properties. We can investigate different sensitivity to specific excitation, for instance, infrared light or near infrared light. So generally this technology is quite useful. In many different cases, we can, for instance, estimate that this approach is useful for production control, for validation, for quality test, or even for a simple demonstration of properties of the treated water produced by customers even in the home environment. So this the multiplicity of application for this approach. So now time for this short presentation is over. To conclude, I tried to reflect all this equation what I asked in the beginning of this presentation. If you have any specific questions, either about the measurement approach or the result what we receive for this particular case, I will be happy to answer them. Now it depends on the organizer of the seminars. And many thanks for your attention.